All right, welcome back to Foundations of Machine Learning. This is Module 8 on maximum likelihood estimation. So where are we right now in the course? Let's just level set. We're entering into cluster 3, which is going to be about maximum likelihood estimation and expectation maximization, or MLE and EM. More specifically, we're in Module 8 currently. So previously, we just came out of modules 4 and 5, which introduced us to the idea of supervised regression, both in the linear form and the logistic form. We used both for classification in the end, and we saw that both of them had a function of risk estimation, which we tried to minimize. After today, we're going to go into modules 9 and 10, which are going to introduce the idea of latent variables. These are variables that we model in our world, but that we don't have access to. They're hidden to us, they're latent. And so we're going to use expectation maximization to solve that problem, and that's all going to be built on today's core ideas in MLE. So for now, we're going to turn data into parameter estimates, theta. We're going to read and plot likelihoods, and then we're going to connect likelihoods to decision-based or decision-aligned metrics. So by the end of this module, you ought to be able to define likelihood and maximum likelihood estimation in precise language. You'll be able to recognize and maybe even write down the likelihood and log likelihood for simple models like Bernoulli Gaussian. You'll be able to compute and visualize MLEs from data using Python, again using our favorites, pandas, NumPy, matplotlib. You will compare models using held out log likelihood and cross entropy, and this will be tied to decision contexts. And then you will name at least 2 threats to valid likelihood-based inference, like leakage and model mismatch. In a lot of ways, this covers the same kinds of ideas that we saw previously with regression, but we're going to keep on graduating into more and more different kinds of models to solve subtly different kinds of problems. So let's role play for a moment. We are running a campaign. We work for a nonprofit, and we are running kind of like an email donation campaign program. Like this is around the end of the year or the early part of the next year, and the email is coming through asking for donations, asking for support, and so on. So we're working for that kind of organization. And what we want to kind of test out a new subject line. Maybe the subject line is match your gift today, exclamation point. That seems like the kind of thing one would send out. So for every email, we're going to have a couple of features. We're going to have things we can measure, inputs, which is X as usual, which is the features of the recipient, which we're going to ignore for today. We're not going to ignore the recipient today, but we're going to ignore like what these features are. Like maybe we have information about their education background or their age or something like that, but it's not necessary to know right now. And then we have, like again, a binary output, Y. So Y is an element of either 0 or 1. 1 meaning true, they clicked the donation link within, say, 48 hours, and 0 otherwise. So all of this really comes from our use case and our stakeholders. So someone in our organization decided that Match Your Gift Today is sort of the intervention that we want to try to test in the world. Somebody else decided that 48 hours is a reasonable time to estimate whether or not they're going to click the donation link. Regardless, we're going to send the email to N people, and we're going to record their clicks. And this is going to form our data set from which we can learn a model. The decision we want to make after we've done this testing is whether or not we ship the new subject line to everyone or just keep the old one. So again, N is the number of people we're testing with. It could be as few as a few dozen, maybe a few hundred, depending on the size of our nonprofit. But we're not going to send an email to absolutely everybody if the subject line is not sufficient in some way. So as usual, we still have different kinds of errors we can make. There's false positives and false negatives, and each of them carry a slightly different cost to us, the organization. So we have the error of saying this is a way better subject line than the previous one, and it's actually not any better. Then we've wasted effort, we've wasted sending an email out, and we've maybe made our potential donors fatigued. But is a false negative would be, actually like the model says this measured gift today is no better than a previous email subject line approach, and but it actually would be. So we missed an opportunity to like send a more engaging email, and then therefore we missed possible donations. So the risk of annoying our donors with an extra email that isn't necessarily any good, versus the risk of not actually obtaining donations to our important nonprofit work. Those risks are different. We have to be able to weigh them. So we're going to basically treat each email as a Bernoulli trial with a parameter p, which is the probability of click. So remember, Bernoulli distributions are just the distribution where we have a probability p of a positive outcome, and the probability of a negative outcome is 1 minus p. Those are the only two outcomes in a Bernoulli trial, and the probabilities have to sum to 1. Today we're going to use maximum likelihood to actually estimate the value of p, like what is the actual probability that this works. And then, as we should, we're going to use held out log likelihood and cross entropy to compare subject lines. So this is our data generating process. We have a usually unknown story that produces data in the world. So, each recipient will click on a link with a probability p that is independent, right? So this is one of the assumptions that we have to make clear. Whether one donor clicks on the link and another donor clicks on a link, those are not causal on each other, right? Like we're assuming that these people are sitting at their computers by themselves, and the probability, like one person clicking a link won't change another person's probability of clicking a link. We're going to build a model. This is going to take a form that looks very similar to mathematically that we saw previously with our functions. Instead of having a f of a theta of x, which could define a linear regression or a logistic regression, now we have p, because p is like just to hammer home the point that we're trying to estimate the probability of something. So this is going to be a simplified mathematical family that we're going to choose to approximate the data generating process. This process is a Bernoulli. So the parameter that we can change, theta, is p. And we're going to try to guess the probability of clicking on a link or not. The numbers we can, again, data is our parameters. Maybe there's a 10% chance that somebody clicks on the link. Maybe there's a 25% chance. That's what we're going to try to find out. So likelihood is usually defined in these terms. We have capital L is a function of theta, semicolon d. We talked a little bit about semicolon notationally in a previous module. This kind of serves the purpose of given, because we're given the stuff on the right of it, or we're given the data set D. This is provided to us. But this isn't like a probability function where the probability of theta like depends on D in the way that a conditional probability would. So normally when we see a semicolon, that means like we're estimating the likelihood of theta, and we're provided with the data set. So the data set are fixed, the parameters are variable, and then the likelihood, which takes this form, is essentially the probability of a data set using the parameters that we can adjust for that probability distribution. So we're going to use likelihood to score how compatible each parameter is with the observed data. And for now, if we're dealing with a Bernoulli distribution, we only have one parameter, which is the probability that they're going to click the link. So we have likelihood, but we're going to talk a lot about log likelihood. So just to make sure we understand why we're doing that, we often deal with log likelihood, or log of L, instead of raw likelihood. So we can do this for a few reasons. One reason is, it has the same maximizer. So because the log function is strictly increasing, so as you increase the value you pass into log, as that value increases, the value of log also goes up. So increasing whatever you pass into it, its maximum will also be a maximum for the log of that thing. So whatever value of theta maximizes L will also maximize log of L. Okay, so in other words, the theta, like the parameter, let's see, this is exactly the same function. Actually, no, it's not, sorry, the log. So the parameter that maximizes the log function will maximize the log of that function, which is what I just said. And one of the reasons so that kind of is not really the reason we're going to go from linear to log, but that kind of satisfies us that since we're trying to optimize something, optimizing in the log space will be the same thing as optimizing in our regular linear space. So here's where we get into the reasons why we use log. So for like independent, identically distributed data, so the data, like I mentioned before, from a scenario where people clicking, like the probability of one person clicking is the same as another person clicking, and there's no effect of one person clicking on the other. So they're independent and they're identical. Or the probability of them clicking, not affecting someone else clicking, is the independence assumption, and the assumption that everyone has the same probability of clicking is the identical distribution assumption. Anyways, so for that kind of data that we're assuming, the likelihood overall of the data is going to be the product of the probabilities of each of the data points, right? So we have n data points. We'll have a probability of the first data point, we'll have a probability of the second data point, and the third and the fourth and the fifth. And strictly speaking, the probability of the whole data set will be that we observe the first data point, and we also observe the second one, and we also observe the third one. So it's a conjunction, which means we have to multiply these probabilities together. And as you so first of all, just in terms of computation, multiplication is more expensive or more costly to your computer than just doing sums. So in some sense, taking the log of the likelihood means we can convert those products of linear probabilities to a sum of log probabilities, right? So assuming that the log function isn't too expensive, this can actually save you some time. Even if you don't make that assumption, which is not always the case, a sum of a bunch of different terms will be very easy for us to differentiate. You'll remember from previous modules that we're going to want to compute gradients for things so that we can move along a surface in a direction of maximum optimization. So we're going to want to do differentials at some point, and differentials over a bunch of different terms means we can just differentiate every term separately, whereas a big conjoined product of a lot of different factors can be more challenging. But also because we've kind of broken things out into different terms, this also means it's easier somewhat to reason about the influence of individual different data points. It's easier to implement a lot of the time. So just practically, that's one reason to do it. It's also numerically more stable. So when we're dealing with probabilities, all of them are going to be smaller than 1. The probability of any particular data point will be very small. And in a lot of realistic scenarios, that probability will be excruciatingly small indeed. And when you're multiplying together even relatively large probabilities, as you're multiplying more and more data, these numbers, like the product, gets smaller and smaller and smaller. And at some point you run into like numerical stability problems where our computers just can't store the precision needed effectively, and we end up having all kinds of possible challenges. And so that's the second reason. So we have, both of these are fairly practical issues, but practical issues matter to us. So before we were dealing with losses, we had mean squared error loss, we had a logistic loss, and in both of those cases we wanted to adjust our parameters to minimize the loss on average, to minimize the problem on average. So because these we want to maximize the probability of a data set, like the probability that a data set is observed, basically tells us how attuned the parameters are to that data set. So we want to maximize the actual data we're observing, but we're used to minimizing losses when we're doing our objective functions. So that's simply achieved by taking this negative sign. So maximizing the likelihood is basically the same thing as maximizing the log likelihood we mentioned a moment ago, which is the same thing as minimizing the negative of the log likelihood. Okay, so now we can go ahead and fit in our losses for our. This is our loss indicated by our script L for this particular task. Let's take a moment and just remember how things can go wrong. Imagine you're trying to train a classifier and you train it on all of the label data. So we haven't split anything up into training and testing yet. And then we compute the likelihood and accuracy on the same data. So how likely it is that somebody's clicking on our emails. And then we can declare, well, like our model is very accurate in like the probability of the data we are observing and all of the data we've collected is very high. Therefore, this parameterization or this model is a really good representation of the data because this model like expects to see this data. That's why it gives it such a high probability. That might be fine in some situations where we're not actually doing modeling and we're not doing machine learning. You're just estimating some kind of quantity on the data itself. There might be various scenarios where that might be the case. But if you're doing modeling and you want to use these probabilities to make predictions, like in our setup, we're going to have to separate our training and testing, just like we saw before with regression, because all of that data we had in our test set will inform the parameters of our Bernoulli distribution, and then therefore the Bernoulli distribution will already have kind of seen a lot of the data that it's being tested on, and just like we saw before, this is a form of cheating. So we don't want to evaluate on unseen data, like ever. So like even though we're translating into a different form of model now, like this kind of one of these golden rules persists. We have the problem of a direction of inference. So just because our parameterization theta gives us a high probability of the data set D, this does not mean that we have a high probability of theta given D. This is actually very subtle, but you'll notice in this little declaration over here, I say our model is extremely likely or accurate. Someone might use likely and accurate as interchangeable. Our model is extremely likely. But technically, this means this quantity down here. What is the probability of this model, given the data? And we're not talking about how probable the model is, at least not yet. Although this quantity will come into play later, but that's not what this person who's making this claim is trying to claim. Okay, so the model isn't really likely, at least not in what they're trying to say, but the data are likely in what they're trying to say. And then there's a model mismatch, right? So, or at least the potential of one. So like a misspecified model can still be like very sharp. So in other words, it can still give a very high probability to our particular data set, but it can still be wrong in general. So small changes to that data set, like if we sampled other data and got a slightly different distribution of data, suddenly our model might give very low probabilities because it's too sharp. It's too tuned just to the data set itself. So like these are just high level things, and they're mostly just warnings about how we talk about our experiments or lack thereof. So likelihood will be a useful scoring rule. It will be used in our training, and it can even be used, like I mentioned, in certain other forms of science, but it's not necessarily a guarantee of truth. We're still dealing with just samples, so we still need splits and baselines and robustness checks. So our standard approaches to machine learning, again, they persist. So now I'm going to define maximum likelihood estimation. So here we have our microscope, so you can tell that we're going to get into the weeds a little bit now. Once again, we have a data set. Now we're not doing any sort of classification or supervised learning. This is more of a form of unsupervised learning. So we're just given X. These are IID samples from some model, the probability of X. Or rather, this is not actually from this model. So these parameters theta, like we assume like there's one true value of these parameters in the world, and we're going to try to estimate what those are. So like I mentioned a moment ago, the overall likelihood of our parameters provided with the data is going to be the probabilities of each of the data points all multiplied together, and the log likelihood is going to be the sum of the log probabilities of each of those individual data points. So this is where the definition comes in. The maximum likelihood estimator, or MLE for short, is going to be the parameterization theta that maximizes the log likelihood. In other words, there's a particular setting of our parameter that gives me the highest probability in total over every data point that I have in my data set. Okay, so in some sense, that particular value of theta, which I call theta hat sub MLE, is the best model that represents the data D. So here's a little bit of an idea. If you ever find some other parameter, now we're calling it theta prime, and theta prime gives you a higher log likelihood for the data than the theta hat we presumably found. In some sense, that means that the parameterization theta prime is like more insistent that the data set is true, right? Or in other words, theta prime, this other parameterization, is more confident that the data set is true. Or it says, for a third expression, that D is the most likely to happen, right? So it expects D more than theta hat does. And if that's the case, all of those things mean the same thing. If that's the case, then theta prime, this other parameterization, is better than theta hat. Okay, so that's why, like, we're just going to find the version of theta in the entire infinite space of possible thetas that maximize this log likelihood. So we're going to see some concrete examples now. This is back to our clicking example. So now we have our y's, like whether they click or not, and we're going to provide these as kind of a signal to our training. So we have our data, we have our model. Our model is a Bernoulli distribution with the parameterization is p, so theta and p is the same thing now, and y is derived from this distribution. So we'll have a data set, and the data set is, this might be kind of complicated, so I'm going to go this a little bit slowly. So here we have n data samples, right? Like some people click, the ith person might click, the I plus 1th person might not click. We have samples for each of these. If the ith person clicks, that means that y sub I is 1, and then this entire term becomes p times 1 minus p to the 1 minus y sub I. But because y sub I is 1, 1 minus 1 is 0. This parenthetical raised to 0 becomes 1. And again, remember y sub I is 1. So this entire data point is represented just by the probability p. Now consider the other case, the only other case, where y sub I is 0. So they did not click on the link. If that's the case, then we have p to the 0. So p to the 0 becomes 1. So this entire factor becomes 1. Then we have 1 minus p to the 1 minus 0. Well, 1 minus 0 is just 1. So that means we just keep this entire parenthetical. And then the entire data point is represented by 1 minus p, which is exactly what we want, right? Because p represents the probability of positive, and 1 minus p is the probability of negative or 0. So we seem to be in good shape here. This is kind of like the switching function we saw previously with the logistic regression, except before we had it with 2 terms, and now we're doing it within one term. So this can be represented in another way. This might be less intuitive, but I'm going to leave this as an exercise, actually. Well, maybe I'll go over it now. Consider that we have a certain number of instances where y sub I is positive, right? So every time we encounter a y sub I being positive, we multiply our ongoing product by p. And on the other hand, we're going to have the rest of the data where y is not positive is going to be all the instances where we multiply our ongoing product by 1 minus p. So this entire expression can be represented this way, because we have the total number of instances of positive y. We have p, times p times p times p, that number of times, times the probability of a negative case. For every instance where y sub I is not 1, which is all of our data except the cases where it's positive. I hope that makes sense. I'm happy to work this out with you on paper if need be. So let k be this quantity that we just summed over here. So the sum of all the instances where y sub I is positive. This will be the actual number of clicks in our overall data set. Okay. So now we're going to take the log of this function. So the log of this function, again, we have p to the k times 1 minus p to the n minus k, right, is how we insert k, or we transform this function to be in terms of k. Okay. Now, when we do this, a log of a product of this quantity times this quantity, the log of those two quantities multiplied by each other is going to be the same as the log of the first plus the log of the second. The log of p to the k plus the log of everything else here. Well, the log of p to the k is going to be, we bring the k down, so it's k times log of p, right? And the log of a quantity raised to a power is going to be that power times log of that quantity. So the n minus k from here comes down, we multiply by log of 1 minus p, and we're done. This is just following the basic rules of logarithms. Okay, so before we do any calculus, I want to pause and just reconfirm why we're going to be setting a derivative to 0 in the first place, because we haven't seen that in the previous kind of approach to risk or empirical risk minimization. So the log likelihood is a function of p, and we're looking for the value of p that makes the observed data most likely. So it's like a maximum of the curve. We want to change p until we get the probability of p to be at the highest point, the maximum of a curve. Right? This is kind of the inverse of what we saw previously. But in calculus, the maxima and minima, the highest points and the lowest points, are going to occur at what's called stationary points. So a stationary point is where the slope of the derivative is 0. Okay, so when you climb up a mountain, you're kind of going like the direction is maybe positive and positive and positive, and then it hits the very peak where there's no more direction you can go where it's positive, so the differential is 0, and then you keep on going the other way down the other side of the mountain, and then the derivative goes negative. Okay. This is also true of minima, like we saw earlier with the empirical risk minimization. You're going down into that bowl until you hit the very, very bottom. So the derivative is negative, 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 and it gets to the very bottom where you kind of level out. And then if you were to keep on going up the other side, the derivatives would start to increase. So if we set the derivative of a likelihood function to 0, that will tell us the location where we're at what I called before was the stationary point. And then that will give us, by definition in this case, the point where p maximizes this function. Okay, so I hope that's clear. So we're actually going to be taking the derivative of the log likelihood with respect to p, and we'll set it to 0. Okay, so here's on the left the derivative of log likelihood with respect to p, and we're going to set the whole thing over to 0. So this derivative has two terms. It has k over p, and it has that comes from the successes, and it has minus n minus k over 1 minus p, and this comes from the failures. So when we set this equal to 0 and solve for this, this will be relatively straightforward, right? I'm going to leave this as an exercise for you just for fun, but what we want is we want p to be on the left side, and we want kind of everything else to be on the right side, right? So we might move n minus k divided by 1 minus p over to the right side, or to put it another way, we might add n minus k divided by 1 minus p to both the left and the right to keep it equal. That would give us k divided by p equals n minus k over 1 minus p. And then we can sort of cross multiply. You've seen this before where you kind of multiply both sides by p. This will cancel out the p on the left side, introduce a new p on the right side. And then taking a few extra steps, again, I mentioned I was going to leave this for you as an exercise. You can figure out what p is in terms of just k. which is the total number of successes, and n, which is the total size of the data set. So just to hammer home this idea, here we have P. Here we have the likelihood for a Bernoulli process P. You can see that this dashed line indicates where the point is maximum. You can imagine, we're trying to optimize things and we're taking the derivatives. If we're moving up this curve from the left, the derivatives are positive. They keep on being positive, but eventually the degree of rising slows down, and we end up kind of hitting zero. Zero is where we kind of level off, and the derivative of this very point is zero because it's a flat, and there's no change. And then we keep on going on the other side. We start falling down. The derivative turns negative, which we wouldn't like anyway. And earlier we mentioned before how maximizing the linear space, in this case just the likelihood, is the same thing as maximizing the log likelihood. You can check out the code as usual. You can see that this point is the same for each of these curves. This curve over here is just the log likelihood of the Bernoulli process. So that's the case where we're dealing with Bernoulli. We're dealing with just a binary outcome. It's either true or false. But now let's try to climb another curve, which is a Gaussian. So now we're not going to deal with binary classes. We're going to deal with trying to estimate the probability of some real valued quantity. So maybe we're trying to estimate the probability of people's heights in centimeters, but this can be any real valued quantity, right? The amount of returns you're going to make on an investment, the grade you're going to get in a class, et cetera, et cetera. Assuming those are Gaussian. So you probably know that a Gaussian is the same thing as a normal curve. Well, I'll show you a picture of that in a second just to refresh your memory, but I assume you remember this. So normal curve, it looks like the bell curve. It has two parameters, mu and sigma. Mu is the mean of the distribution. Sigma is its standard deviation. Sigma squared is its variance. And I can assume that I have lots and lots of samples drawn from this Gaussian distribution, and I can assume that those are also independent and identically distributed. So this somewhat complicated looking function over here is the Gaussian function, or the normal function. You don't need to get into it too much. You don't need to memorize it, certainly. But you can see how we have a couple of parameters. We have our sigmas and we have our mu, and this entire thing is the probability of observing a data point x sub I in this distribution. Now, as before, what is the likelihood of this parameterization provided with this data set? That's still going to be the probability of observing the first data point, x sub 1, times the probability of observing the second data point, x sub 2, and so on and so on and so on, all the way through our n data points. For the same reasons that we took the log of the product of probabilities in the Bernoulli case, we're going to do the same thing with the Gaussian. I'm going to leave this for now, but you can do this as an exercise if you wish. Applying the log to this product is going to be the sum of the logs of this of the Gaussian, and then if you keep on going, this entire thing transforms into this equation. Right? We're going to ignore constants, but there it is. Skipping even further, so between this log likelihood and the optimization, we're actually going to do we're going to take the derivatives of this log likelihood function with respect to mu on one side, and the derivative of this log likelihood function with regards to sigma on the other side. We're going to do that once in each case. In each case, we're going to take those derivatives of the log likelihood with regards to one of the parameters, set that to 0 for the same reasons we saw with Bernoulli, and then basically to solve the equation. So just move things around until mu is left on one side and everything else is left on the other. And it'll break down into what we're familiar with anyway, right? So the best possible value of mu for a Gaussian distribution under this maximum likelihood estimation process is just going to be the average value of x sub I. Like almost by definition, but that's what we get, so we're not really surprised. And maybe somewhat more surprised, but maybe not really, the best possible value for sigma squared, or variance, which we get from taking the log likelihood of a data set, And then taking the derivative of that with regards to sigma squared and setting that to 0 and solving, that gives us the average of the squared difference between the true mean mu, or the estimated mean mu rather, and an individual data set, the average of these. These are just the definitions for mu and sigma squared in the first case, in like a sample-based Gaussian. So we're not surprised, but I wanted to go through those steps anyway, skipping some of the details which are irrelevant. So this is what the Gaussians look like. So we have a sample of data represented by this blue histogram in the background. And we have a couple of different fits of that data, some optimum fits. So if we just set mu to be the average value of all of the x's that are behind this histogram, and we set the value of sigma squared to be the sample, standard deviation squared or variance of all of these samples, then we get this orange curve. And as you can kind of see here, this orange curve looks like a pretty good estimate for that histogram of real data. It's not perfect, obviously, but it doesn't have to be. But now we can stretch things at least. So we're going to keep the mean fixed, but we're going to squish sigma inwards and stretch it outwards. And as you can see, like this green curve where sigma is too small, like we have too small of a standard deviation, that's not a very good representation for the breadth of this data. And if we stretch out sigma and make the Gaussian very kind of all big and stretched out, like this reddish dotted curve over here, then that's also really not a good representation for this histogram. So we can kind of see that the best representation of the data is the one that follows the MLE strategy. So one more example, Poisson counts. So Poisson is basically a measure of the number of events within a fixed time window. So like how many password reset requests can you expect per hour? So we have a lot of data here again. We have n data points, and these data points are going to be integers. So we expect like a integral amount. So either a 0 password reset request, or 1 or 2 or 3 or 4 or so on. So our data, we can assume now, derives from a Poisson distribution with parameter lambda. We can again assume that these are independent and identically distributed. And then given these assumptions, again, another formula that you're not going to have to memorize, but the formula for Poisson is over here on the right, this little fraction, e to the minus lambda times lambda to the power of k sub I divided by k sub I factorial. Okay, where k sub I is the number of observed events within the time window, and then we have n time windows. And again, we have our probability of observing the event. We have n probabilities of observing each of those n events. The overall likelihood of the entire data set is the product of each of those probabilities multiplied with each other, all the way down. So for the same reasons as before, we prefer log likelihood to just likelihood. So we apply that to this product. We can drop constants that don't depend on lambda, and then we end up getting this formula. I'm skipping over some details now because those details are not going to be relevant to you. So we get this, and then we can rewrite it. We can factor things out, and we get the sum of k sub I over all of our n data points times log of lambda, which is our parameter, minus n of lambda plus some constant. Now again, we want to find the parameter that is the best parameter for a Poisson distribution given all this, or provided with all this data we have. Okay, so we're always, as always, we're trying to find a parameterization that gives us the best model for the data we have. So the same as before, we take our log likelihood, which we've worked out here. We take the derivative of that log likelihood with regards to one of our parameters, and then set that to 0. You can leave this as another exercise for why the derivative of all of this stuff here at the bottom with regards to lambda is equal to these two terms. But you can kind of, at the very least, you can see that the derivative of n times lambda with regards to lambda is going to be just n. So that's the second term over here. Set it all to 0, move things around a little bit. This one's going to be pretty easy because we can add n to both sides. So we get sigma sub I of all the ki's over lambda equals n. And then we just multiply both sides by lambda and divide both sides by n. So we get lambda on one side, we get everything else on the other, which is just this. I would really recommend that you take your notebook, that you're putting all this stuff down. It's easier if you have a paper notebook, I guess, than Obsidian or Chrome or Notion. But walk through some of these steps and just for your own benefit to become more comfortable with these steps. So again, maximum likelihood estimation. This general approach of trying to maximize the likelihood of with a data set, a particular set of parameters. Works if we're dealing with Bernoulli distribution, it works if we're dealing with Gaussian distributions, and it works if we're dealing with Poisson distributions. Just a few more examples to wrap up. So going back to our original MLE for click-through rates. We have a tiny synthetic data set inspired by our email campaign. Each row is one email sent, and then the supervised signal we're trying to optimize is whether it's clicked or not. Okay, so here's how I generate the data. We're going to have n samples. The true probability behind the scenes that we don't actually know is going to be 0.3. Okay, we're going to generate all this fake data, and then in the end, it's going to look like this. And summarizing this data, we have 28 instances where they don't click and 12 instances where they do click. Or, in this case, the indices match up. False and true respectively, or negative and positive respectively. Here's some code. So this is where we actually perform a little bit of estimation. So if you recall, for Bernoulli, we have this sort of log likelihood of positive events here, which is the first term, k times the log of p. And then we have the negative term for this log likelihood, which is n minus k times log of 1 minus p. We worked out why this is the case mathematically on a previous slide, so you can go back and check it out. But this is just the Python version of the math we saw a moment ago. Okay, so we're just implementing the log likelihood, and then we're going to draw up the figure, and that gives us this. This is a figure very similar to the one I showed you a moment ago. So this estimates that here's our true click-through rate, p hat, and it's the point where this curve is maximized, which is coincidentally the same. Not so coincidentally. So yeah, you can observe that the log likelihood is maximized at exactly the empirical click rate. So work that out for yourself. Bernoulli, now we go into Gaussian. Imagine we measured the time in seconds it took students to submit an online quiz after it opens. This will become increasingly familiar to you. Each row will be a student's submission time, and we're going to model these times as Gaussian for now. So there's going to be some standardization and other steps we do in real life, but let's just take that as read. So here we have our fictional data set of 30 students. And here we have the submission time. So the first student submits after just over 2 minutes. The second student submits after just before 89 seconds, and so on. Then we have our code. Our code is it just follows what we did before. We have our MLE estimate of mu, which we computed to be just the average of all of the observations. So we just take the average of all of our submit time seconds. So that's the mean. That's going to be stored as mu. The sigma squared, which we found previously, is going to be the actual observation, the x sub I, minus the mu that we just computed. All of that's going to be squared, and it's going to be the average of all of those square differences. That's going to be our sigma squared. We saw this in a mathematical form. Now we see it in Python. And sigma squared is the square of sigma, so we just take the square root to get sigma. And then we can just describe it. So our estimate for mu hat is 120.5 seconds. Our estimate for sigma hat, our best value for sigma, is about 22.9. And that translates to this orange curve over here. And as you can kind of see, this is a fairly good representation of our real data, represented by our blue histogram in the background there. And indeed, this is the best fit of a Gaussian, assuming a Gaussian, and so on, of this data. So again, maximum likelihood estimation picks the parameters that best explain the observed histogram under this Gaussian assumption. So now we're going to have a little demo, the numerical MLE demo, a logistic regression in one dimension. So far, our examples had these kind of closed form MLEs. So it's closed form because we could derive the optimum setting, like the best value of mu, the best value of sigma in the Gaussian case, or the best value of lambda in the Poisson case. These were all closed form. We had them from a formula directly. But for many machine learning models, so when we saw logistic regression previously, when we see neural networks in the future, there's no algebraic solution. There's no formula that tells us this is the perfect value of theta, whatever theta is, that will fit this data the best. We're going to have to approximate and find the best value of theta numerically, step by step, approximately, like we saw with logistic regression. So first, continue a tiny one-dimensional logistic regression. Feature X will be some measure of a relevance score for every email. Our label will be a binary label like we had before with logistic regression. This is whether they clicked or not. Our model will be the probability using the parameters theta, trying to estimate what is the probability that they'll click given whatever our input features are. So again, like we saw in the last module, this is going to be based on a linear function of X, with its own parameters, W and B, like we've seen several times now. All of this will be passed through the sigmoid function represented by sigma. This will give us that nice nonlinear, curvy S-shaped function. And again, here's just what the sigma curve is. We saw this previously. Here are our parameters. So if we fix B for the moment, so B is set, we're going to change it. There's going to be no closed form solution to find the maximum likelihood estimate of W, right? We're going to have to go step by step because we're using logistic regression like we did in the previous module. So here's some code that's just going to describe this process. What this function is for different possible values of W. We're going to try to get higher and higher and get bigger and bigger values of the log likelihood of our parameter W using the data we have at our disposal. Okay, so if we have W, which is like the slope of our line, that's too negative, our log likelihoods are going to be very small. But as we get closer and closer to our value of W, our parameter, that maximizes our log likelihood, or in other words, would minimize our negative log likelihood, then this will be the best value of W for us. Okay, so here we can find this optimum value of W hat, with a simple grid search over candidate values. But in real life, like we saw in the previous module, we're going to use this gradient-based approximation, like gradient descent in this case, because we're climbing up this curve as opposed to falling down into it. We might use stochastic gradient descent to find the minimum negative log likelihood or its allegory. There's something called Newton's method, which you might have seen previously. It's outside the scope of this class, but Newton's method can also help us find optima, but take it as read. We could use various methods to find these optima. But the end result is that MLE will become this sort of generic numerical optimization problem once we can compute the log likelihood and its gradient. So now we have our maximum likelihood estimation. We want to see whether or not this is going to actually align with our decisions. So consider the average negative log likelihood, or NLL, on a held out set of data. So now we're thinking of our test set. So we have, or this held out set will be a validation for now. So N sub val is the number of data points we have in our validation data set. And the average negative log likelihood will be, like here's the negative. The average is because we're summing over all of the values, and we're dividing by the total number of values we have, or the number of data points we have. And then we have the log of the probability of observing that particular data point in our held out validation data set. So for binary classification, this is exactly the cross entropy loss. We saw this previously, so it's the same as always. But we want to make sure this is aligning with our decisions. So consider, the overconfident wrong predictions should get very large penalties. This is good when bad decisions are going to be costly. And when we're comparing two models on these held out a negative log likelihood or average negative log likelihood answers. We want to still ask the question, which model is going to assign higher probability to what actually happened. Okay, and just like we saw before during training, whichever model gives a higher probability to what we actually observe is a better model for what we actually observe, so we prefer it. Just a little bit of another ethics nudge. I'm going to keep on trying to come back to this because, again, increasingly machine learning in context requires us to be responsible. If we have biased data in some way, that means our likelihoods are also going to be biased. Okay, so if the data we're estimating our probabilities on come from groups that are maybe the majority class, maybe there's underrepresented parts of our population that are just not normally part of our data sets. They're not normally emailed, or they're not usually part of these campaigns, then whatever their behavior is not going to be part of the machine learning process. Therefore, we're never going to learn anything about them. So these probabilities won't represent them. In other words, the maximum likelihood estimation will faithfully reproduce whatever biases exist in our data collection process. And similarly, if we have actual examples of bias, MLE will just learn those biases directly. So we can mitigate this in various ways. We can always check performance or the likelihood by these subgroups. So if there's a particular part of the population that you want to check, wait, does a model actually represent their behavior well? Then just check the performance on data derived from that group, right? Collect data from that group. There are other kinds of fairness constraints we can apply, but we can get to that later. And then, of course, is privacy and re-identification. So if your data has all of these user logs that describes when they clicked it, what they clicked, browser knowledge, OS knowledge, that kind of thing, then you can leak information. So the model might learn a lot of information that incorporates all these other factors that maybe are relevant to you, maybe they're not relevant to you, but regardless, they start to paint a pretty clear picture of who this person is. And you want to avoid that, so minimize the data. Like if you don't need to know whether someone's using Firefox or Chrome, then just don't store that information because it's not useful to you, but it might be useful to a hacker. So minimize, aggregate where possible, preserve privacy where possible, and so on. As always, we have a quick check. So pause the video if you want, but really go to the slides that are posted on the course website and answer the questions that you can find there. I'm not going to do this in one breath, but I'm going to mention the properties of maximum likelihood estimation. That's sort of a summary of everything we just talked about. So as the number of samples we have from the world approaches infinity, and this hasn't been achieved yet, but in theory, imagine it could be, then the approximation of our parameters, theta hat, will converge in probability to the actual true parameter theta star, right? So theta star is a parameter of the world, and the more and more data we derive from the world, the more and more our parameters can approach how the world generates data. Okay, this assumes, of course, that we have access to all the parameters. It consists of asymptotic normality, so this is not going to be really relevant to you, but for large n, like the distribution of the parameters is approximately derived from Gaussian, where the center of this Gaussian is the optimum parameter value, and everything else is Fisher information. This is not going to make too much sense to you now, but we might come back to this later in this course. It's fairly efficient, maximum likelihood estimation. So amongst a broad class of reasonable estimators, MLE attains the smallest possible variance in large samples. So it's very efficient. It's invariant. So if your estimate sigma hat is the maximum likelihood estimate of your parameters, and phi is a function g over the whole parameter space, is like a one-to-one reparameterization. So you're transforming your parameters into some other parameter space. Then g of your best parameters in theta is going to be the maximum likelihood estimate of your best parameters in phi. So this might not make much relevance to you either, but one of my graduate students is literally doing a PhD thesis on this kind of scenario. You can transform spaces to other spaces with parameters. right now, it might not make too much sense, but as we get deeper and deeper, this is going to be an important part of MLE. So we're not going to prove this. This is more of an extension, if anything. But this hopefully will explain why MLE is so popular. In summary, these likelihood scores will basically compute how compatible a parameter choice is with observed data. Maximum likelihood estimation will choose the parameters that will maximize log likelihood, and it'll often match the empirical statistics we're familiar with. So in the Bernoulli case, the values we computed in a closed form from maximum likelihood estimation were exactly the parameters of P we wanted in Bernoulli for positive or negative outcomes. Similarly, in the Gaussian, we did all this special work just to end up with the sample mean and the sample variance. Assuming in this case 1 over n. We talked a bit about sample variance versus population variance, but that's a bit detailed. So in practice, we're going to evaluate our models using held out NLL or cross entropy, which will respect our pipelines. So we'll do clean splits, we'll have baselines, we'll have clear decision contexts. So MLE is powerful, but it can be fragile in some situations. When can it be fragile? So if our assumptions about the data generating process are wrong, or if they have extra parameters we can't guess at, or if our model is wrong, so we chose a Gaussian, but we should have chosen a different shape of distribution, or maybe our pipeline is wrong, then there's always going to be a part in the process where everything we've done, we can go step by step, but we won't get decent results because we made mistakes at one of these points. So be aware of that, and feel free to ask me questions, and I'm looking forward to the next set of modules. See you next time.